Welcome to today's GATE video lecture. I am G. Vasumathi, working as Assistant Professor in EC Department at our S.A.E. Engineering College. In today's session, I am going to explain Section 5 Digital Circuits, which comes under ECE syllabus. So nothing but logic gates and their static implementation use. So in section 5 we have 5 categories of topics: number system representation, sequential circuits, data converters, semiconductor memories, computer organization. In that I am going to explain logic gates implementations using static Cmos. So before entering into the topic, we need to know what is CMOS, what is the importance of CMOS, why we are choosing CMOS to design a logic gates. So CMOS is a technology which is widely used to design digital logic circuits as well as digital ICs. So it uses two pairs of transistors, that is complementary pairs of transistors, NMOS, CMOS. So N-type MOSFET as well as P-type MOSFET. So the learning impact of this will help you to understand the core principles of VLSI design in a very good way, as well as it enables us to design a low power logic circuits using a static CMOS. So now before entering in depth to the topic, we'll see what makes static CMOS the go-to choice of logic gates. Obviously, it is a very great choice for designing digital system. So the reasons behind selecting CMOS is static CMOS consumes very low power because during switching only it consumes power. Other time there is no direct path created, so it will reduces static power consumption. Of course, it uses two different complementary pair of transistors, so it reduces leakage and enhances noise margin. It provides high noise margin. This complementary circuit leads to better performance and better switching characteristics. These features collectively make CMOS as a better choice and dominant choice for designing logic gates and digital logic circuits. Advantages and disadvantages. Already we discussed numerous points why we are selecting CMOS as a static CMOS as a design concept. So here the collective advantages are it consumes very less power, there is no direct path, so it reduces leakage current, also it gives high noise margin as well as high speed performance. Next, the only two drawbacks of CMOS, designing logic gates using CMOS is it increases the count of transistor because it requires, static CMOS requires 2 N transistors for its design. In the case of dynamic CMOS, it requires N plus 2 transistors, so that comparatively it requires high transistor count. Also, it makes the area larger, so chip area is large in a static CMOS. And the second, it uses more number of transistors, so the design speed will be degraded little bit. However, it reduces static power, so we can use it very effectively. Applications of static CMOS. So it has numerous applications in digital circuits design. So very few examples of applications is it is used in the design of microprocessor, microcontroller, digital logic circuits implementation, as well as low power and battery operated devices. So static CMOS, already we discussed, it uses complementary pair of transistors, PMOS as well as NMOS. So here the basic structure of static CMOS is defined as two networks, pull-up network and pull-down network. So in pull-up network it uses PMOS. Now let me discuss why PMOS is selected for pull-up as well as why NMOS is selected for pull-down. So we will discuss it in the next video. Yes, structure of static CMOS. So this is our generic structure of static CMOS. while designing any gates or digital circuits using static CMOS, we need to use it as a basic concept. Yes, so here one pull-up network which is connected to VDD, it uses PMOS for its design, and the output is immediately taken across pull-up network and pull-down network which uses NMOS for its design. So pull-down network is connected to ground. So input is common to both pull-up and pull-down. It shares the input. So always input is applied to pull-down, which can be shared with pull-up network. Yes. So the reason for using PMOS, as I said in the previous slide, the reasons for using PMOS at pull-up and NMOS at pull-down here. Yes, efficient logic level transformation. Because in NMOS strongly process 0 because it is connected near to ground, so that it can pass strong 0 as well as it will pass weak 1. So that PMOS will passes strong 1 because it is nearly connected to VDD, so it passes strongly 1 and poor 0. So by this concept we can get strong 0 as well as strong 1 transformation using PMOS as well as NMOS. Second thing, the complementary operation of PMOS and NMOS ensures there is no direct path between VDD to ground. However, it reduces switching delay as well as it reduces direct path, in the sense it reduces static power. Yes, so this is the reason for using PMOS at pull-up and NMOS at pull-down. Other reasons includes power efficiency. So the low power dissipation will lead to better design. Also, it increases power efficiency. The next reason for using pull-up at PMOS at pull-up and NMOS at pull-down is reliable digital logic design. Why? Because transformation of logic strong 0 passing strong 0 as well as strong 1 leads to better design methodology. Yes. Next, we are exactly entering into our topic logic gates implementations using static CMOS. We will discuss basic gates one by one. First, I start with inverter. So, this is the general structure of inverter using static CMOS. Static CMOS structure contains PUN, PDN. So obviously PUN uses PMOS and PDN uses NMOS. For inverter logic, we have only one input which is inverted at the output. We know very well. Yes. So for this concept, we need one single input. So the input is shared between NMOS as well as PMOS. The output is immediately taken here. The output will be your complement of input, A bar. So this is what the design structure of inverter using static CMOS. The next basic gates is NAND gate design using static CMOS inverter. In NAND gate, we are going to use two inputs, A and B, and output. So the basic structure of NAND gate will be look like this, symbol of NAND gate, which contains two inputs A and B and one output Y. So for two input NAND gate, the output will be A dot B the whole complement. So inversion of your AND gate is nothing but your NAND gate. So for this two input connection, we need to implement a structure with two PMOS and two NMOS. So PMOS for dot logic, any dot like logic and operation and all, we need to use PMOS as parallel and NMOS as series. So this is the design concept. Whenever we are using dot operation, we need to connect PMOS in a parallel way and NMOS in a series connection. So this is the exact principles behind designing NAND gate using static CMOS. Now here I will draw a NAND gate structure using static CMOS. So VDD, immediately we need to connect two PMOS transistor in parallel with the inputs A and B. Then next to it, immediately we need to get output Y, which is nothing but A dot B the whole complement. Next, two NMOS connected to output of second NMOS is connected to ground, which has the inputs A and B. So this is what the structure of NAND gate using static CMOS. The next design is NOR gate implementation using static CMOS. Already discussed, in dot logic, PMOS is connected in parallel and NMOS is connected in series. For NOR gate implementation, it is quite opposite to NAND gate. So for plus logic, we need to connect. For a plus logic, we need to connect PMOS as a series connection and NMOS will be connected in parallel. So for implementing any plus logic, we need to follow this rule. So this is the exact CMOS structure of your NOR gate. So in this structure, we are designing two input NOR gate. So it contains inputs A and B and output is Y, which is nothing but A plus B the whole complement. Now see this design. PMOS are connected in series and NMOS are connected in parallel. So not by taking a separate ground, we can combine it to a single ground also. So both were correct concept only. So this is the design of NOR gate using static CMOS. Next, so this is a consolidated design of your 2-input NAND gate as well as 2-input NOR gate. So see this design and the contrast and similarities between them. It shares the 2 inputs A and B. The connections of PMOS as well as NMOS differs for dot logic as well as plus logic. For plus logic, PMOS looks in series connection and NMOS looks in parallel connection, vice versa for NAND operation. The next is a CMOS implementation of AND gate. Most possibly, CMOS will design any complementary logic directly. But for non-complementary logic like AND gate or gate, we need to include one inverter at its output. So this is what the thing we need to change for NAND and AND. So here I am using a 2-input AND gate. Let me see how the design will looks. Yes, this is nothing but a structure of your NAND gate, 2-input NAND gate, which we will discuss in the previous section. Now this NAND structure output is connected to one NOT gate structure to convert the output from A dot B the whole complement into A dot B. Gate at the output of NAND gate will result in AND gate operation, nothing but A dot B. So in this way, for designing OR gate, we need to connect an inverter across the output of your NOR gate. We will discuss it in the next slide. The next thing, example, here I am showing one example to design a complex CMOS gate. Here the output is D plus A dot B plus C, the whole complement. Yes, so already we discussed CMOS is best choice for implementing a complementary logic. If we wish any normal logic to be implemented in CMOS, we need to use NOT gate, that is CMOS inverter at its output. Yes, now this connections is a composition of dot logic as well as plus logic. So let me see. So it is nothing but A dot. So it is in dot logic. So A is connected in parallel. The next, here see this logic B plus C. So in this expression, B and C are connected in series. For B plus C, we need to connect it in series. For dot operation, we need to connect PMOS in parallel. Next, the D is parallel to these two expressions. Next, the reverse design, that is complementary design of NMOS shown here. Yes, here D is connected in parallel because it is composed with plus logic, and A is connected in series. B plus C is connected in parallel because of plus and dot logic composition. So this is what designing any complex structure using CMOS. I hope you understand these concepts clearly. The next gate questions on logic implementation using static CMOS. We'll discuss one by one. The truth table which accurately explains the operation of CMOS NOT gate is, so here are the choices. Option A describes when input is 0, PMOS is off, NMOS is on. The output will be 1. Yes, of course, I agree with this first point. Input is 0, output is 1. Because CMOS inverter produces complementary input at its output, right? Next, you check the conditions one by one so that we can select appropriate answer. So next, the input is 1, the output is 0. Now, we need to check whether PMOS and NMOS are work in a correct way. For 0 input, PMOS is off. For first case, for 0 input, PMOS is off and NMOS is on. Usually, PMOS will turns on when input is 0. PMOS will turns on when input is 0. NMOS will turns on when input is 1. So, wrong one. Yes, now the concept is exactly contrast. For the input 0, PMOS is off. For input 0, NMOS is on. So, the first option is not in our constraint. We'll move on to the second option. Here, input 0, output 1, input 1, output 0. So, input and outputs are matched exactly for inverter concept. See this, PMOS is on, NMOS is off. For 1 also PMOS is on. So, this is also not correct. The next condition, for input 0, output is 1. Yes, of course. But for 0 input, PMOS should be on, NMOS should be off. See this first. Both PMOS and NMOS are at on condition. This is also not under our option. The exact thing is option D. Why? Input is 0, PMOS is on, NMOS is off. Output will be inverted. Next, for input 1, output should be 0. Yes, of course, it is as it is. PMOS is off, NMOS is on. So, this is what the option for explaining operation of inverter. Next question. In CMOS logic circuit, the PMOS transistor access, we already discussed these things in the structure of PMOS, CMOS. so that we can exactly write. In CMOS logic, PMOS is always connected at pull-up network. In CMOS logic, NMOS is always connected to pull-down network. We already discussed the reasons behind this thing. Yes. The fourth question. In CMOS logic circuit, the switching operation occurs because NMOS transistor, read the options like both NMOSFET and PMOSFET turns off simultaneously for input 0. So no. So either PMOS or NMOS will be on at a time. We discussed there is no direct path between NMOS and PMOS because of its complementary working. Yes. So the first point is not correct. The second point, both NMOSFET and PMOSFET turns on simultaneously for input 0 and turns off simultaneously. No, this is also not agreed. Next, the NMOS transistor turns on and PMOS transistor turns off for input 1. Yes, exactly. And NMOS transistor turns off and PMOS transistor turns on for input 0. So this is what the option. Why? Because PMOS and NMOS will not turn on at a time simultaneously. So that it will maintain high level transformation of logics. Also, it works in a complementary manner. So option C is the correct. When both, we will discuss the next question. When both NMOS and PMOS transistors of CMOS logic design are on or off, either on or off condition, the output is, so it is nothing but crowbar or contention state. We say it as crowbar or contention state. We'll see why it is called so. So here is the explanation for that crowbar state. When both pull-up as well as pull-down transistors are on, high impedance or floating output states will result, because this exists when both transistors are turned on or off simultaneously. This condition is called contention because this output leads to static power dissipation. In CMOS design, our ultimate aim is to avoid static power dissipation as well as direct path between PMOS and NMOS, but in this case, it eliminates our constraint on static power because it dissipates high static power when both NMOS and PMOS are turned on. So this is what crowbar or contention state. Next, sketch a CMOS gate that implements the following function. So here, see here a composed logic of plus and dot logic exists. Now I'll show you how to design this logic using static CMOS. Before designing, look at this expression. Variables A, B, C are in plus operation, that is A plus B plus C, and E and F are product with these terms, also plus G dot H. Here for this circuit we need 7 inputs A, B, C, E, F, G and H. Now I start the design with PMOS. PMOS is immediately connected to VDD. So here first I'll show how A, B, C are connected because it comes under plus logic. So obviously it has to follow series connection. Exactly. The next expression is connected in parallel with A plus B plus C because here a dot operation exists. So how to connect these things? So we can connect E and F in a series way which is parallel to A plus B plus C. Next, for GS, again a plus operation exists, so I can connect like this. G dot H is connected in parallel. So this is what the design of pull up network. For pull down network, we need to use NMOS. So the connections are reversed as in the case of NMOS. Pull. Yes, here one CMOS structure is shown. So they are expecting what is the output for this logic or structure. See, A is connected in parallel with D and E. So these structure are connected in parallel with B and C. So what will be the output? Either we need to compute with PMOS or we can clearly get the output with NMOS contributions, right? So while obtaining output of any logic circuit, we need to consider either PMOS or NMOS to avoid confusion. Now it looks like A is parallel with D plus E and B and C are connected in parallel and it is plus logic with the above structure. So now I am going to write the output of the given structure. Yes, it is nothing but V out is equal to A dot D plus E plus BC. So this is what the output for the given structure. Next, CMOS is sometimes referred to as option A, capacitive metal oxide semiconductor, capacitive symmetry metal oxide semiconductor, complementary symmetry metal oxide semiconductor, complementary symmetry. So here the correct answer is given as complementary symmetry metal oxide. The reason is also given in the same slide. So the next question, what will be the effect of output voltage if positions of NMOS and PMOS CMOS inverters are exchanged? So the output also will get reversed because while reversing the circuit, the output also get reversed. Next, so here also three different structures are given. The output of these three structures can be computed as let me explain this structure first. So here A and B are connected in series, C and D are connected in series. So these two transistors, PMOS transistors, are connected in series, but these two are parallel to each other. So the output will be A plus B dot C plus D the whole complement. So this is what. So in this circuit I am considering only PMOS series parallel connection. Based on it I can write the output. So you can cross verify your answer with the NMOS structure too. So here A and B are connected parallel. Of course, for parallel connection, plus operation should exist. Next, C and D are connected as parallel. Of course, so it is nothing but C plus D, but these structures are connected in series. So the output is nothing but A plus B dot C plus D the whole part. Moving on to the next circuit. Here, the next circuit is A and B are connected in series, which is parallel with C bar. So we can include any variable, C bar, X bar, Y bar, we can include anything. And for static design, no need to complicate with that inverted inputs or anything. We can directly write the output based on the inputs and its combination, series parallel combination. So here the output, I denoted it as Y. So it is nothing but A plus B dot C bar the whole complement. So this is what the output for the given structure. Now look into the third structure. Here three PMOS transistors, namely A, C, D, are connected in series. Sorry, A is connected in parallel with B and C and D are connected in series with E. What will be the output? So, nothing but AB dot C plus D and E. So, this is what the output for the given structure. Next question. If the NMOS and PMOS of CMOS inverters are interchanged and the output is measured at not inverted state, then the output will be, yes, before answering this question, we need to remember what is CMOS inverter structure. So, we know very well. So, for CMOS inverter, only one input, so that one PMOS and one NMOS is used for the design. PMOS is connected to VDD and NMOS is connected to ground. The output is taken immediately across PMOS. Now, in the question, NMOS and PMOS are reversed. So, say this is the source terminal of this PMOS transistor and this one will be the gate terminal of PMOS transistor and this one will be the drain terminal of PMOS transistor. So, the output is taken immediately across the drain terminal of, note this point, drain terminal of PMOS. Right. Now, look at this NMOS. In NMOS, drain terminal is connected near to output. This is what your gate terminal, and source terminal is connected to ground because of its pull down property. Yes. Now, the output comes across the drain of PMOS as well as the drain of NMOS. Now see the options. Source of both transistor, no. If it is exchanged, in the sense, what will happen? So here one NMOS transistor is connected and here one PMOS transistor is connected and the terminals are interchanged. It is nothing but A, the output is here. Here a source, here the drain, here it is gate. Again, it is nothing but source and it is nothing but drain and it is nothing but gate. So, here the terminals also get changed. So, here is drain, gate, source. So, exactly the output comes across drain of NMOS and source of PMOS. In normal case, we can get output across the drain of each NMOS and PMOS transistor. For the inverse case, so this is what the correct option. Next. In CMOS inverters, the output is measured at, obviously in the previous diagram I shown you. So both the output is got across the drain of your PMOS transistor. In CMOS inverters, the output is measured at drain of NMOS and ground. I'll discuss about many interesting concepts on CMOS design and different gates design using static CMOS. I hope everyone can understand. We'll meet you on the next gate video session. Thank you to all.